Hello friend, welcome to Math A to Z. This is the second class of basic ring theory. In the first class, we discuss up to divisor of 0 or a ring with 0 divisor, and you get the link of the first class in the description box of this video. Now we are going to discuss the next part of the basic ring theory. Now come to the subject. We know that a ring Z6 equal to 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus. Here 2 plus into 3 plus equal to 0 plus. Also 4 plus into 3 plus equal to 0 plus. So we can write 2 plus into 3 plus equal to 4 plus into 3 plus. But this does not imply 2 plus equal to 4 plus. So we see that cancellation law does not hold. Now we say that a ring without 0 divisor, is hold cancellation law, or if a ring hold cancellation law, then it must be without 0 divisor. So in the form of a theorem, we state an important theorem as a ring R is without 0 divisor if and only the cancellation law is hold in R. Now we go to the proof of this important theorem. Here we let the ring R is without 0 divisor, and we have to prove cancellation law hold. Let A, B, C be any 3 elements of the ring, and A, B equal to A, C, A dot B equal to A dot C, and we have to prove that B equal to C, that is let cancellation law hold. Now from this relation we get A dot B minus C equal to 0. Since here we let A is a non-zero element. Now since A not equal to 0 and R is without 0 divisor, so we must have B minus C equal to 0, that is B equal to C. So from this relation we get B equal to C, that is from this to this we say that the ring or in a ring the left cancellation law hold. Similarly we can prove the right cancellation law hold in this ring also. Now we prove the converse part of this theorem, which is here cancellation law hold. Cancellation law hold imply R is without zero divisor. Without zero divisor. For proving this, we let A dot B equal to 0, where A, B a non-zero element. Now if we prove B equal to 0, then the ring must be without zero divisor. From this relation, we can write A dot B equal to A dot 0, since A dot 0 equal to 0 from the property of 0 element. Now, from the left cancellation law, we can write B equal to 0. So, from the cancellation law, we get the ring without zero divisor. Okay, this is a very important theorem of the basic ring theory. Now, we get to another important theorem of ring, which is a non-trivial finite ring having no zero divisor. No zero divisor is a ring with unity. Ring with unity. Here, this is very important word, finite ring, and we now discuss which is non-trivial ring. If R equal to 0, only 0 element, here 0 plus 0 equal to 0 and 0 dot 0 equal to 0, and this set together with plus and dot forms or follow all the properties of ring. So R plus dot is a ring. This is zero ring. Sorry, this is trivial. This is trivial. And if in a ring R, A dot B equal to 0 for all A, B belongs to R, and plus is defined as usual, then this ring is also called, now 1 second please, yes, then this ring is called zero ring. Here definition of dot is A dot B equal to 0 for all A B belongs to R, and the definition of plus is as usual. Now, which is non-trivial ring? A ring contains at least 2 elements, that is 0 and at least 1 non-zero element. Then this ring is called non-trivial ring. Now we come to the proof of this theorem. Here R, ring R is finite. Let R equal to A0, A1, A2 to An, n plus 1 number of elements. N plus 1 number of elements. Here must be a 0 element. Let this be 0 element be a 0 element. Now we multiply all the element of R by A1 from the left, also by A1 from the right. We get A1 dot A0, A1 dot A1, A1 dot A1, and A0 dot A1, A1 dot A1, An dot A1. We get two set of product. All the element must be belongs to R. Here this element A1 dot A0 equal to A0, because this is the property of 0 element. And among them there must be A1, also among them there must be A1. Let A1 dot AP equal to A1 here, and let AQ dot A1 equal to A1 here. Here this and here this. And these n elements, this n plus 1 element must be distinct, because if A1 dot AI equal to A1 dot AJ, then we get A1 dot AI minus AJ equal to 0, and here A1 not equal to 0 element, because A0 is a 0 element. Then we must have AI minus AJ equal to 0. Since in the statement the ring having no divisor of 0, no 0 divisor, so AI equal to AJ, and if AI equal to AJ, then the ring contains n element less than n plus 1, and this contradict our assumption. So we must have all these elements are distinct, and all these elements are similarly distinct. Now we get this relation and this relation. If we let B be an arbitrary element of the ring, then here also we get A1 dot AR equal to B, and AS dot A1 equal to B, because any one of them is B and any one of them is B. Let A1 dot AR is B, and here AS dot A1 B is B. Now we consider the product B dot AP equal to B dot AP equal to AS dot A1 dot AP, and by associative law AS dot A1 dot AP equal to AS dot A1 dot AP equal to A1, and AS dot A1 equal to B. So we get for arbitrary B belongs to R, there is B dot AP equal to B. Similarly, AQ dot B equal to AQ dot A1 dot AR, this is B. By associative law, AQ dot A1 dot AR and AQ dot A1, this means A1 dot AR and A1 dot AR, this is equal to B. Now, for arbitrary element B, we get two relations as B dot AP equal to B and AQ dot B equal to B. Also, 0 dot AP equal to 0 from the property of 0 element and AQ dot 0 equal to 0. So if B not equal to 0 or B equal to 0, then in the both case this relation is hold. That is, for arbitrary element B, these two relations must be true. Now we consider AP is also any element of R. Then we replace AP in place of B and here we replace AP in place of B and we get AQ dot AP equal to A. Also, AQ belongs to R, be any element, so we can replace AQ. We can replace B by AQ. Then also we get AQ from this. AQ dot AP equal to AQ. But left hand side of two relations are same. So we must have AP equal to AQ. And since AP equal to AQ, then we say that AP equal to AQ, then we say that B into AP equal to B equal to AP into B and AQ equal to AP. So here we put AP and from these two relations, for all B belongs to R, from these two relations we say that AP is the unity of R. So we can say that the ring R with unity. Okay, this is the proof of this theorem. Now we get an important example of ring theory. If you consider the set of matrix 2A 0 0 2B, A B belongs to Z, set of integers. This is R. This is obviously a ring with respect to matrix addition and multiplication, and this ring is with zero divisor and this ring is without unity. If E belongs to R such that if this element is equal to A, such that A into E equal to E into A equal to A. Let E equal to 2x 0 0 2 y. Now AE equal to A imply 2A 0 0 2B 2x 0 0 2y equal to 2a 0 0 2, and multiplying them, if we get the corresponding element, we get 4ax equal to 2a and 4by equal to 2b, imply x equal to 2x equal to 1 and 2y equal to 1. That is x equal to half, y equal to half. That is, this does not belong to z and this does not belong to z. So we can say that this does not belong to this ring. So the ring not contain unity. So the ring is without unity. Now if we consider two elements like 2 into 2 0 0 2 into 0, this is A, that is 4 0 0 0, and B 0 0 0 6, then AB equal to, multiplying A and B we get 0 0 0 0, that is 0 matrix. But here A not equal to 0 and B also not equal to 0. So the ring is without unity and with 0 divisor. This is an important important example of ring. But if AB belongs to R or AB belongs to Q, then this contains divisor of 0, but this is with unity. Okay. Now go to the second example. Second example is R. R is A, B, 2B, A, such that A, B belongs to R, set of real number, and this is also a ring, and this ring also contains 0 divisor. 0 divisor. Let this element is equal to B, A, B, 2B, A, and consider an element B equal to P, Q, 2Q, P. AB equal to PQ, 2Q, P equal to, and it B 0 0 0 0. Multiplication of two non-zero matrix is a 0 matrix. We assume it. Now from the multiplication we get AP plus 2BQ equal to 0 and 2BP plus 2AQ equal to 0. Clearly, this is a homogeneous system of equation. And this system have non-zero solution if determinant a to b to a equal to 0. That is 2a square minus 4b square equal to 0. That is a square minus 2b square equal to 0. Now, if we put a equal to plus minus root 2 and b equal to plus minus 1, then we get the matrix as root 2, 1 and 2 root 2, 2 root 2 and minus root 2 minus 1, and this is 2 minus 2 and minus root 2. Please accept it. This and this. Now, multiplication of these two matrices is obviously be 0, 0, 0, 0. So we say that these two non-zero matrices, this is not equal to 0 and this also be not equal to 0. This multiplication of two non-zero matrices is a 0 matrix. So this ring also contains divisor of 0. Okay. Now we come to an important definition of ring theory. An element in R, a non-zero element in R, if there exists B belongs to R such that A dot B equal to B dot A equal to I, where ring with unity I, then B is equal to A inverse. That is, if in a ring a non-zero element is invertible, then this element is called unit element. Unit element of the ring. Correct? So, if in a ring an element whose multiplicative inverse exists, then this element is called unit or unit element in this ring. And if an element in a ring be unit, then the multiplicative inverse of this element must be unit. Let A not equal to 0 belongs to R being unit element, and if possible let A has two inverse B and C. Now from the definition of inverse, A dot B equal to B dot A equal to I. Also, A dot C equal to C dot A equal to I. Now B dot A dot C, we consider this product equal to B dot A dot C. Here A dot C equal to I, that is B dot I, and here B dot A equal to I, that is I dot C. From the property of unity I, we get B equal to C. So the inverse of an unit element must be unique. Now the unit element of the ring Z are only 1 and minus 1, and other element is not unique in Z. All the element of R plus dot, all the element but non-zero element are unit. All the element of Q plus dot, set of rational number, are unit, but non-zero element is not unit element. Similarly, in Z6, 2 plus 3 plus 4 plus, these are not unit element, but 1 plus 5 plus are 2 unit element. In Z5, 1 plus 2 plus 3 plus 4 plus are all unit element, and in MNR, this is a ring of n cross n matrix, and entries of the element of matrix are each real number. All the element of this ring which are non-singular are unit element. Now we took a very easy theorem that the zero element in a ring is not unit. Zero element in a ring is not unit. If possible, let 0 belongs to R, be the zero element, and 0 inverse is the inverse of 0. So the property of inverse element, we get 0 dot 0 inverse equal to 0 inverse dot 0 equal to I. Also we get 0 into 0 inverse equal to 0 inverse into 0 equal to 0, because this is the property of 0 element. So from this two relations we can write I equal to 0, but this is not possible since this ring must be non-trivial, since a ring with unity must be non-trivial. Now we move to another theorem, which is if A be a unit in R with unity, then A must have no divisor of 0. A must have no divisor of 0. Let A dot B equal to 0. Here A not equal to 0 because A is unit element. A is unit element, so A must be non-zero. Since A is unit, imply A inverse exists. And since A inverse exists, we can multiply both sides multiply from the left in both sides of the relation. We get A inverse dot A dot B equal to A inverse dot 0. And from this A inverse dot A dot B equal to 0, that is I dot B equal to 0, imply B equal to 0. That is A dot B equal to 0, imply B equal to 0, while A not equal to 0. This relation shows that an element A is unit in R. Then A must have no zero divisor. And another important theorem we can prove here, and which is this theorem. Every non-zero element in a finite ring, having no zero divisor, is unit. Can also be an important word, finite. Every non-zero element in a finite ring having no zero divisor is unit. Now let R be a ring with n plus 1 element, A0, A1, n. Here must be a zero element. A0, and since this is finite and this ring having no zero divisor, then we can prove, or we proved already in the previous theorem, this ring must contains unity I. Now if we multiply by A1 from the left and again from the right, then we get A1, A0, A1, 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 and from the right we get A0, A1, 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 AN, A1. This n plus 1 element, and from this n plus 1 element, 1 must be I, and here also 1 must be I, but this is not I because it is 0, since A0 is 0 element, and here also this is equal to 0. Now we can let A1 AU equal to I, and here AB A1 equal to I. Now we consider the property, but consider the product AV dot A1 dot A equal to AB dot A1 dot AU, imply AV dot this is a1 dot au equal to y and ab dot a1 equal to y, imply ab equal to au. If ab equal to au, then we get this is au and it is also be au. So a1 dot au equal to au dot a1 equal to I. So au must be a1 inverse. So a1 inverse exists, that is a1 which is not equal to 0 is unit in R. Similarly, by multiplying both sides from the left and from the right by a2, we can show a2 is also unit, and similarly all the elements which are not 0 are also unit in ring. This is also an important theorem about divisor of 0 and unit. Now, if we collect all the unit of a ring, if we collect all the unit of a ring, let R plus dot be a ring, and we collect all the unit of the ring, and we get the set H such that A belongs to R, A inverse exists. Then we can say that, or we can prove that this set must be a group, must be form a group. With respect to dot. Now we prove this. Let A and B belongs to H, then A inverse, B inverse exist, and these are also belongs to H, because we know that A inverse whole inverse equal to A belongs to H, and B inverse whole inverse equal to B belongs to H. Now, if AB belongs to H, and then we have to show A dot B belongs to H to show the closure property of H. And to show A dot B belongs to H, we have to show the inverse of A dot B is also exist. Now A dot B dot B inverse dot A inverse equal to A B dot B inverse A inverse equal to A I A inverse A dot A inverse equal to I. Similarly, B inverse A inverse dot A dot B equal to I. So A dot B whole inverse equal to B inverse A inverse belongs to R. So A dot B must be unit, that is A dot B belongs to H, and this is the closure property. Associative property with respect to dot must be held in H because it hold in R, and associative property is the hereditary property. Now come to the identity property. Identity property, let E or I be the identity element of R. Then we know that I into I equal to I. So inverse of identity is I also. So I belongs to H. So identity of H is also the identity of R. Now we come to the inverse property of H. We know that if A belongs to H, then A inverse exists and in R. So A into A inverse equal to A inverse into A equal to I, and we from this relation we say that A inverse whole inverse equal to A. That is inverse of A inverse, this is belongs to H. That is inverse of A inverse exists, that is inverse property will also hold. So all the four property of proof satisfied by H. So we can say that the set of all units in a ring R with unity forms a group with respect to multiplication. Now we discuss a most important example of this chapter, which is the ring Zn plus n dot n modulo n. Okay, and in this ring an element m bar belongs to Zn is unit if and only GCD of Mn equal to 1. That is, if GCD of Mn equal to 1, then m bar is unit in Zn, and if m bar is unit in Zn, then must be GCD of Mn equal to 1. And the proof of or the solution of this example is, we first let m bar is unit in Zn. Zn be a ring with unity 1 plus. Since m bar is unit, so there must exist u bar belongs to Zn such that m bar into u bar equal to 1 plus. That is mu congruence to 1 mod n, that is mu minus 1 congruence to 0 mod n, that is mu minus 1 equal to Lv, where u, v both belongs to set of integer, imply mu minus Lv equal to 1, imply mu plus n into minus v equal to 1. This relation gives GCD of Mn equal to 1. Okay, now we let GCD of Mn equal to 1. If GCD of Mn equal to 1, then there exists UB belongs to Z such that UM plus Vn equal to 1. That is UM minus 1 equal to minus Vn. That is UM minus 1 congruent to 0 mod n. That is UM congruent to 1 mod n. Imply, if U class belongs to Zn, then U class into M class equal to 1 class. That is U class is the inverse of M class. But if U class does not belong to Zn, then we must have U congruent to R mod n, where R class belongs to imply MU congruent to MR mod n, imply M class into U class congruent to M class into R class mod n. That is M class into U class congruent to M class into R class congruent to 1 class. That is, sorry, this is not mod. That is M class into R class congruent to 1 class, and R class is the unit. R class is the inverse of M class. So we get an important theorem that if M class belongs to Zn, is unit in Zn, then we must have GCD of Mn equal to 1. So the number of unit in Zn plus n dot is given by phi of n, that is less than n and prime to n. Less than n and prime to n. This is Euler phi concept. This is Euler phi concept. Okay, now at last we discuss an important example, and this is the last example of the class. We consider the ring of integral quaternion. Integral quaternion, that is H equal to A. This type of set, this type of matrix, A plus IB minus C plus ID and C plus ID and A minus ID, such that A, B, C, D belongs to Z. Set of integer. Here A belongs to H is unit, that is A inverse exists if if determinant A not equal to 0, that is non-singular, and determinant A equal to clearly a square plus b square plus c square plus d square not equal to 0, must be not equal to 0. Now if we find A inverse, then we get 1 by a square plus b square plus c square plus d square into matrix A minus ib, c minus id, minus c minus id, a plus ib, and this belongs to H only if a square plus b square plus c square plus d square equal to 1. If this is not equal to 1, then this does not belong to H. And a square plus b square plus c square plus d square equal to 1, then we get 8 different cases. The first case A, B, C, D is 1, 0, 0, 0. Second case -1, 0, 0, 0. Third case 0, 1, 0, 0, 0, -1, 0, 0, 0, 0, 1, 0, 0, 0, -1, 0, and 0, 0, 0, 1, 0, 0, 0, -1. These 8 different cases, and from these 8 values of A, B, C, D, E, we get only 8 matrices as 1, 0, 0, 1, -1, 0, 0, -1, I 0, 0, minus I, minus I 0, 0 I, 0, 1, -1, 0, 0, -1, 1, 0, 0 I 0, and 0 minus I 0. Only these 8 elements in H is unit element, are unit element, and obviously these 8 elements together forms a group, and this group is called unit quaternion, and this group is denoted by U8. Okay, and this is the end of the second class of basic ring theory. Thank you for watching, and please subscribe my channel and give a lots of like and comment please. Thank you for watching.